Okay. Uh, I think the other day we were discussing about the power series solutions for differential equations. And what we had done was we had simply discussed what do we mean by power series, first of all, in the sense that we had seen that any series of the form summation Cn x to the power n, where n varies from 0 to infinity. Such a series we had termed as a power series, right? And when you expand this series, you get terms like C0 plus C1x plus C2x square and so on and so forth. It's an infinite series, right? So all these C0, C1, C2, they are all coefficients in this infinite series and they are constants. So we are assuming that they're real numbers right now, okay? Now, when it comes to differential equations, as I had said that, why this is required is that every differential equation, or in other words, we might come across differential equations that cannot be solved in the standard methods that we have learned so far to solve differential equations. Okay, so we need to change the methods of solving such equations. And introducing power series method is one such method of solving a differential equation. Okay. Now, as I was just telling you, I had given a hint also, and I asked you to try things. What we normally do is like, I think the differential equation that we took the other day was y dash plus 2y equal to 0. Okay. Now, the usual results, the usual the usual observations or the results that we have proved for differential equations, they never get violated even if we talk of solution in terms of power series, in the sense that uh, this is a first order differential equation, right? And for a first order differential equation, we know that it can have only one arbitrary constant. Similarly, second order differential equation will have two arbitrary constants, okay, and so on and so forth. So those results still remain valid even when we talk of power series solutions. How we are going to do that, we are going to learn today now, okay? Now, for this differential equation, I had asked you to solve it by the method because it's a first order with constant coefficient. So I think you people only gave me that it's a variable separable form. So I think it was like you can solve it as writing like this by separating the variables. And we had seen that the solution turns out to be something like this. Am I right?
Yes, ma'am.
Yes, ma'am.
I can write as y equal to e to the power minus 2x plus c, which is actually nothing but minus e to the power minus 2x into e to the power c. Now, since c is a constant of integration, so e to the power c becomes an arbitrary constant. So your solution can be written like this. Am I right? Right. So
Yes,
that
ma'am.
means I know that if I solve this differential equation, then this is how we have learned so far how to solve it. Okay. Now, when I say we are talking of power series solution of this differential equation, that means my differential equation is still this y dash plus 2y equal to 0. Okay. Now I assume, I say, let y equal to summation Cn xn, n from 0 to infinity, be a solution of this differential equation. Okay, so let's number this 1. So I say, let this be a solution of this differential equation 1. Okay, now that means what? That means I have assumed that this is a differential equation. Now, when this is a differential equation, that this is a solution of a differential equation, I'm sorry. So that means what? That means my y, which I have assumed to be this, actually satisfies the differential equation. Okay. Now, when it satisfies, means what? That means with this as y, I can find my y dash, which will be nothing but the derivative of this power series. And we discussed it in the last class that derivative of a power series means term-wise differentiation of that power series. Okay. So your y dash is going to be c1 plus 2c2x and so on and so forth. Okay. Now, this is like writing every term specifically, or I can use the generalized notations also, in the sense that my y I can write as Cn xn n from 0 to infinity. This was my y. So my y dash will be nothing but summation. I can write this as uh, n c2 x to the power n minus 1, n varying from 1 to infinity. Is that right?
Yes, ma'am.
This will be my y dash, because now you can differentiate from this only. See, the derivative here will be n cn x to the power n minus 1. But because my leading term is a constant term, and when we take the derivative here, it's going to be 0. That means my terms are going to start from the index when n varies from 1 to infinity. Now, this is also important. So what I'm going to do is, we'll come to it also as we come to the solution part, in the sense that we can always change this index of summations. That means if I want to have a generalized terms, that means in every term I want my n to vary from 0 to infinity, I can always change this. Okay, how we are going to do this, we'll come to this later on. Now, that means what? That means this, with this y and this y dash, both of them must satisfy my differential equation, in the sense that I must have summation n cn x to the power n minus 1, n from 1 to infinity, plus 2y, right? This was y dash plus 2y. So plus twice summation cn xn, n from 0 to infinity, must be 0. यही होना चाहिए ना,
Yes, ma'am.
because they must satisfy. Now, when we are talking of finding a power series solution, that means starting with a general solution for this particular differential equation, we are going to now find how these coefficients are going to behave, because depending upon the coefficients, we are going to get a solution, right? So when I'm finding a solution, that means I'm starting with a generalized solution. I'm assuming that it is a solution. Therefore, it must satisfy the differential equation. So once it satisfies the differential equation, this is going to give me some relationship amongst the coefficients, using which I will be able to find the values of the coefficient, and hence the typical solution, which is going to be the solution for my differential equation. Is this clear?
Yes, ma'am. So ultimately, we need to find Cn,
Yes,
and then
ultimately we
from
need to find CNs. Right?
yes,
Now,
ma'am.
see, I need to combine these terms, right? How they are going to behave. So for this, in order to combine these two terms, I must have the summation starting from the same number, at least same index, right? See, otherwise, what we could have done, the easiest way is, your y dash was what? C1 plus 2c2x. इस तरह से था ना?
Yes, ma'am.
Plus 3c3x square, and so on and so forth, plus 2y. 2y would have meant 2c0 plus 2c1x plus 2c2x square, and so on and so forth. This was your y. If you write every terms separately, यही होगा, लेफ्ट हैंड साइड y dash plus 2, यही होगा ना?
Yes, ma'am.
Y dash plus 2y. So 2y would have been c naught plus c1x. यही तो है ना हमारा? So y dash means c1 plus 2c2x and so on, plus 2y means 2c naught plus 2c1x plus 2c2x square, and so on and so forth, right? Now this must be equal to 0. This is what I mean when I say that it is a solution, right? Now what we can do is, we can combine similar terms, in the sense that my constant term is nothing but C1 plus twice C naught. These are my constant terms. Then what is the term with X? It's going to be 2C2 plus 2C1, right? What is going to be the terms with X square? It's going to be 3C3 plus 2C2, and so on and so forth, equal to 0. Now, see, when I have sum of positive terms equal to 0, that means each coefficient must be 0, right?
Yes,
So
ma'am.
that means what? I must have C1 plus 2 C naught equal to 0. That means what? I can express my C1 in terms of C naught. Am I right? Similarly, the coefficient of x should also be 0 in the sense that 2C2 plus 2C1 must be 0, which means my C2 must be equal to my minus C1, right? But what is your C1? Your C1 is nothing but minus 2 C naught. See, why we are doing this is, I know that this is a first order differential equation. So it must have only one constant. So what we can do is express each Cn in terms of C naught, so that I'll have only one constant, arbitrary constant C naught. So if my C2 is minus C1, that means this is actually nothing but twice C naught. My C2 is nothing but plus twice C naught. Similarly, I'll have third term 3C3 plus 2C2 equal to 0, which means your C3 is nothing but minus 2 by 3 C2, which means nothing but minus 2 by 3 into 2 C naught, and so on and so forth. Right? Now, this is one way of generalizing the coefficients. The other way is, I go back to my differential equation along with the summation symbol and try to derive a generalized formula from here only. Okay. But to do so, what I need to do is, I need to have the summations starting from the same index. Okay. In the sense that this first term is starting from n equal to 1. The second term is starting from n equal to 0. So obviously the easiest way would be to rewrite the term here so that my summation also starts from n equal to 0. That means what? See, if I am trying to express my summation starting from n equal to 0, that means I am trying to decrease the starting point by 1. Okay, see here in this case, actually right now the starting point is 1, but in this case the starting point is 0. So if I want to change this to 0, that means I am trying to decrease the starting point by 1. Okay, now when we decrease the starting point by 1, we have to increase the index. Okay, so see, this is one thing that you have to keep in mind, whether we are increasing the starting point or decreasing the starting point. If we are decreasing the starting point, we have to increase the summation of index. That means we have to change our n, right? So that means in this case, what we'll do is, we can always change our n to n plus 1. Why? Because we are decreasing the starting point by 1. If it is the other way around, that means if I want to increase, it could be possible that instead of starting from n equal to 1, I want to start from n equal to 2. Okay, so in that case, we are increasing the starting point by 1. So if we are increasing the starting point by 1, we have to decrease the index. So in that case, we'll change n to n minus 1. Is this clear? Because this will be using frequently off and on. Okay. So what we can do is, we can change n to n plus 1. The moment we do this, my first summation now becomes n varying from 0 to infinity. The term here, the first term was what? N. So instead of n now, it will be n plus 1, because I have changed n to n plus 1. Okay. The second term was what? Cn, so it becomes Cn plus 1. Then it was x to the power n minus 1, right? So your n minus 1, now since you are changing n to n plus 1, so your n minus 1 gets changed to n. So this becomes your first term now. The second term was plus twice summation Cn xn, n varying from 0 to infinity equal to 0. Is this step clear? Yes or no? I mean,
Yes,
because
ma'am.
unless and until it is clear, there's no point in moving ahead.
एक्सक्यूज मी
Hmm?
मैम।
हाँ जी।
मैम हमने इसको n+1 से चेंज किया है,
हाँ,
बट अगर ना भी चेंज करे और n की लिमिट हम 0 टू इन्फिनिटी से ही ले, फिर हमारे पास क्या डिफरेंस आएगा सॉल्यूशन
तो
में
हमारे
y
पास
डैश के
C1
लिए?
नहीं आएगा ना, और C0 हमें चाहिए नहीं।
यस मैम। मैम द थिंग इज कि एक टर्म उसकी बढ़ जाएगी, लाइक अगर सी एन रख रहे हैं तो वहाँ पास C0 भी आ जाएगा, पर अगर अल्टीमेटली हमारा क्या था, C1 था
हाँ,
स्टार्टिंग
हमारा
नंबर।
जब हम y डैश ले रहे हैं, सी देखो, जब हम इधर y डैश में जा रहे हैं तो हमारा y डैश C0 से थोड़ी स्टार्ट हो रहा है। सी हमारी सीरीज से मैं हम सीरीज थोड़ी चेंज कर रहे हैं अपनी, हम इसी सीरीज को ही तो एडजस्ट कर रहे हैं ना। तो जब
बट
हम
मैम
y डैश ले रहे हैं तो हमारा लीडिंग टर्म 1 हो गया, देयर इज नो C नॉट हियर।
मैम यहाँ पर सी नोट नहीं है, बट जो हमारा y डैश आया है वो y से आया है,
हाँ
तो देखा जाए तो C0 का डिफरेंशिएशन 0 हो गया हमारा।
हाँ
तो ये
हाँ
0+C1+2C2x ऐसे है ये।
हाँ।
फिर तो मैम हम डायरेक्ट इसको n को 0 से इन्फिनिटी तक कर सकते हैं, सोल्यूशन
नहीं,
को तो कोई डिफरेंस
ये
लगेगा
तो
नहीं।
बाय चांस है कि तुम्हारा लीडिंग टर्म कोफिशिएंट दोनों में 1 है। सपोजिंग कोई कांस्टेंट साथ में होता या प्लस कुछ भी होता, तो
फिर
this
चेंज करना होता।
what you are trying to say is might work here, but it might not work in every differential equation, in every series.
यस मैम।
So we have to have a uniform rule that works everywhere. Okay,
यस
so
मैम।
that's what I'm saying. You have to just keep in mind this thing, whether you are increasing your starting point or decreasing your starting point. If you are decreasing your starting point, this case में कर रहे हैं, we are decreasing our starting point from 1 to 0. So in that case, we have to increase the index. If we are increasing the starting point, we have to decrease the index. और अगर तुम उसमें भी करोगे ना, you will get C0, but हमारे को C1 के साथ 0 चाहिए, मतलब C1 कांस्टेंट टर्म चाहिए, C2 के साथ x चाहिए, so वो प्रॉब्लम रहेगी हमेशा. So it's better to learn the generalized way of changing the indexes of summations. Is this okay?
यस मैम।
Okay. So this becomes my left hand side. I mean, this becomes my differential equation now. Now, of course, I can combine the terms in the sense that my summation now is starting from 0 to infinity, right? Secondly, in both these terms, I have x to the power n. So that means I can retain x to the power n as it is, and I just have to collect their coefficients. So from the first term, the coefficient is n plus 1, cn plus 1, and from the second term, the coefficient is 2cn. Is that right? Now it means this is equal to 0. Now we use the logic in the sense that I have infinite series equated to 0. So what should I have? All the coefficients must be 0. So that means what do I get? N plus 1, Cn plus 1 plus 2Cn must be 0. Is that okay? Because I have sum of a positive term series equal to 0. So each coefficient independently, specifically must be 0. Okay. Now, the moment you have this, I can write my, that means what? My Cn plus 1 actually is nothing but minus 2Cn upon n plus 1. Now, this, what you have derived here, this is called as a recurrence relation. Isn't it a recurrence relation in the sense that I just have to, put n values of n and I'm getting all the coefficients. So I don't have to bother in the sense that when n is 0, what do you get? C1 equal to minus 2. When n is 1, what do you get? Sorry, minus 2 C0. Is that okay? When n is 1, left-hand side becomes what? C2. What is that equal to? Minus 2C1 upon n is 1. So 2, right? But what was C1? Minus 2C0. So this becomes 2 by 2 into 2C0. Okay. when n is 2, what do you get? C3 equal to minus 2 by 3 C2, which is nothing but minus 2 by 3, 2 by 2 into 2 C naught. Right? Obvious question should be कि आप ऐसे क्यों लिख रहे हो? That's because I'm now trying to derive a general formula. See what happens when n is 3. What do you get? C4. Now n is 3 means minus 2 C3 upon 4, which is nothing but minus 2 by 4 into minus minus will make it plus into 2 by 3 into 2 by 2 into 2 by 1 C naught. Are you getting what I'm trying to write?
Yes, ma'am.
Huh? Can you write your Cn now? A generalized formula for Cn?
Ma'am, 2 factorial and C naught.
I want to write now Cn in terms of C naught.
And then 2 by factorial and C naught.
No, it's not just 2 by factorial n. There are so many 2's.
Then
That's why I
to the
did
power
not
n.
use them. They-
Ma'am, 2
Then,
to the power n.
and then
Ma'am,
they're
2 to the power
alternately
n.
plus minus. See, I can write C1 as
Then
minus 2 by 1 C
minus 2
naught.
to the power n.
So what will it be?
Ma'am, minus 2 to the power n by n factorial C naught.
No, we don't write it minus 2 to the power n. It should be minus 1 to the power n, 2 to the power n upon n factorial. Is it right or wrong?
Yes, ma'am, right.
Is that okay? So, but then what was your power series? Your power series was summation Cn x to the power n, n from 1 to infinity. We had assumed this as our solution, for which we have obtained our Cn to be this. That means the power series, which is going to be a solution for this differential equation, is actually nothing but this, n from 0 to infinity. So that means with these as the coefficients, it should be my solution. Now, since you have obtained your values of C1, C2, and so forth, can you just write your solution here? What should be your solution? Y was what? C naught. What is the other term? C1x. How much is your C1? Minus 2 C naught. So that means it should be minus 2 C naught x. Then plus, यही था ना हमारा y तो C naught plus C1x plus C2x square and so on and so forth. So हमारा C naught we have not changed at all, but C1 we have obtained in terms of C naught. We get this. How much is C2?
2C2, 2C naught.
2 C naught. अभी general formula लिख रहे हैं हम. So this becomes 2 C naught x square. How much is C3?
Minus 4 by 3 C naught.
Minus 4 by 3 C naught x cube and so on and so forth. So if I take C naught common, what do you get? 1 minus 2x, है ना?
Yes, ma'am.
2x square minus क्या आएगा साथ में? 4 by 3 x cube
4 by 3 x cube plus 1 by 4 x to the power 4.
and so on and so forth. You know the expansion for e to the power x. Power series expansion for e to the power x. क्या होता है?
Ma'am, 1 plus x square by 2 factorial.
2 factorial
And
plus
so on and so
x.
forth. What will be the power series expansion for e to the power minus 2x?
मैम x को -2x सब्स्टिट्यूट कर देंगे.
हाँ, right. So what do you get?
1 minus 2x,
Uh,
4x square.
I want the final term. And so on and so forth.
1 plus 2x square.
Plus 2x square. Then the next one. Instead of x cubed by 3 factorial, when you replace x by minus 2x, what do you get?
-4/3x cube.
Minus 4 by 3 x cube and so on and so forth. Isn't it this series?
Yes, ma'am.
So basically what you have got is y is equal to c naught e to the power minus 2x. And this was the solution. हमने वेरिएबल सेपरेबल फॉर्म में से भी तो यही निकाली, a e to the power minus 2x. So instead of a, we have a c naught. It's an arbitrary constant. So this was, see, this was a case where we could find the solution anyways. So that's why we started with this kind of an example. You see, we obtained the functional form of the solution by using the method, variable separable method. Now, what is a variable separable method? It is a standard way of solving an ordinary differential equation. So that means we had a differential equation which could be solved using the standard ways. We know the solution, right? But we could solve that differential equation by the power series method also. And we in the end, we observe that they are both equal. That means whether I solve by this method or I solve by this method, I'm getting the same solution for this differential equation. Okay. Now, this was, I mean, we started with this specifically because I wanted to show that they are similar, right? But supposing there is a differential equation which we cannot solve by standard methods or which become too tedious to solve by standard methods of solving. So obviously we have to resort to power series method in that case because it becomes easier. At least we are getting a solution. Okay. So once we have this solution with us, we know that we can solve differential equations by this method also. Now, but the major thing, I mean, which anybody should have pointed out is, what is the guarantee that a given differential equation will have a solution by power series method as well? See, we did not check anything in the beginning. We were given a differential equation. We started with something of this form, okay? And we assumed, that's what I said, the very first thing that I wrote, let this be a solution. That means we are assuming that the differential equation that we are starting with has a power series solution. We did not check anything, right? Okay, now we'll come to that, of course. We have to be sure. See, it's a big effort. We started with just first order differential equation, so it was easy. Imagine if you have a differential equation which is of a higher order and you are solving by power series. So you're going to get some, messy, cumbersome terms. So it's not an easy method also, right? So that means even before we solve, we must learn, number one, whether this differential equation is going to have a solution by power series also or not. Okay. Secondly, the second question that should come to my mind is, if I have a power series, is this power series going to be convergent? Okay. So because ultimately, the moment we talk of infinite series or we talk of sequences, ultimately our objective is to learn whether they are going to be convergent or not, because it is the convergence which is going to play an important role. If it is not convergent, the solution is not of any importance to us. So obviously we are looking for things when they are convergent. Okay. So before we move to the question number 1, we try to answer question number 2 here. Okay, and to talk of the convergence or divergence, we talk of a term which is called as the radius of convergence of a power series. I know you have studied it, right? But like how we define is that if I have a power series of this form, summation Cn xn, n from 0 to infinity, then we define a term rho, which is actually nothing but limit n tending to infinity, the absolute value of the ratio of the coefficient of the nth term to the n plus 1th term. Okay, we define this term rho. Okay, and with this as my power series, I'm assuming that this number rho exists. Now, if it exists, that means what? Rho is finite, or we are assuming that rho is infinite. That means we are assuming that this limit exists. Now, once this limit exists, then I have two options, that this limit can be either finite or infinite. Okay, in case it is infinite, that means in that case, we are writing that my rho is infinity, in case this limit is infinite, right? Now, just remember this rule, that we have this rule, it says that if this limit is 0, that means if rho is 0, then the series diverges for all x not equal to 0. Okay, that means if this limit is 0, this amounts to saying that the series is convergent only when x is 0. यही कह रहे हैं ना हम, the series diverges for all x not equal to 0. That means when does it converge? When x is 0, right? So it's just a matter of, twisting the statement, right? So we are saying that the series diverges for all x equal to 0. Number two, the second situation can be that your rho is a finite term. Okay, the limit exists, but is a finite limit, different from 0, right? So if rho is a finite term, then the power series Cn xn, n from 0 to infinity, this converges if mod x is less than rho, and diverges if mod x is greater than rho. Is this clear? Okay. So that means what? That means in case this rho turns out to be a finite number, then it is going to tell us, the radius or the areas or the values around which that power series is going to be convergent. Okay. So it is going to be convergent if mod x is less than rho. Otherwise, it is going to be divergent. But the third case, if rho is infinity, that was the third possibility. Okay. Now, this is the best possibility because it says that then the series converges for all x. Okay. So that means this is the best scenario. So every time we start with the power series, we start with the power series solution of a differential equation. We solve it in the sense that we make that solution satisfy the differential equation. We obtain the values of the coefficients. And once we have Cn's with us, we can check whether the series is going to be convergent or not. Obviously, we would like our rho to be infinity. Like in the earlier case, what was our Cn? Just look at the solution that we had just obtained. What was my Cn? The general formula that we had derived. It was nothing but minus 1 to the power n, 2 to the power n upon n factorial into C naught. यही था ना हमारा Cn.
Yes, ma'am.
Right. So what will be Cn plus 1? Obviously, minus 1 to the power n plus 1, 2 to the power n plus 1 upon n plus 1 factorial into C naught. Now I want to see what is my rho here. And what is rho? The limit of modulus of Cn upon Cn plus 1. Okay. So in this case, my rho is going to be limit n tending to infinity modulus of Cn. So Cn, you want to write, I can write the whole term upon n factorial into C naught upon Cn plus 1. So upon Cn plus 1 would mean n plus 1 factorial upon minus 1 to the power n plus 1 into 2 to the power n plus 1 C naught. यही हो जाएगा ना? Now what is this equal to? Can you simplify? I'll write it in this box now. So what is rho here equal to? Limit n tending to infinity. What will it be? Just cancel out common terms. Because it's a modulus sign, so minus is not going to make any difference. So what does it turn out to be? बोलो क्या होएगा ये?
Ma'am,
N
1 by
plus
2.
1 by 2.
Anyone can speak.
N plus 1 by 2.
N plus 1 by 2, right? So what is the limit when n tends to infinity in this case? Simple.
Infinity.
What is the limit?
Infinity.
Infinity. And when rho is infinity, what happens?
For
The
all values.
Converges all x.
series is convergent, right? So that means the solution that we obtain for, and that is why you have convergent है, तभी तो convergent किसको converge कर रही है वो series? To e to the power minus 2x. Okay, so that is why we have a well-defined solution both ways for this differential equation. Say, for example, supposing you have, do we have time? Yes, we have time. Supposing you have something like this differential equation, x square y dash, we'll be doing 2 equal to y minus x minus 1. And this is one thing that we want to solve. And the second that we would like to solve is x minus 3 y dash plus 2y equal to 0. These two specific differential equations is supposing we have to solve and see what happens to their solution. Okay, so just look at the second one. Of course, the standard method, the method remains the same. I'm doing the second one first, okay? So we start with let y equal to, you also do it simultaneously now, okay? N from 0 to infinity be a solution of the second differential equation, okay? So that means how much is your y dash? Summation n cn x n minus 1, n from 1 to infinity becomes my y dash, okay, which I can write as summation. Again, I'm now changing the index here only. N from 0 to infinity, n plus 1, cn plus 1, xn. In fact, okay, let's not do it right. I'm sorry, because now I think, let's not do it here. Now I'll explain what happens. Now you substitute with this as your y and this as your y dash. We substitute in the second differential equation. So what do you get? X minus 3 y dash tha na ma? So that means summation n cn x to the power n minus 1 n from 1 to infinity plus, what was the other thing?
Ma'am, plus 2y.
2y.
Plus 2y. N from 0 to infinity. ये है ना? Equal to 0. Now see, when I have first term, I mean, I can split the first term into two terms. Okay? One with x, that means I multiply every term of this series with x, I get one term. I multiply every term of this series with -3, I get another term. Okay, so that means I'm going to get something like n from 1 to infinity, n cn. I have a x here and I have an x minus xn minus 1 here. So if I club the two, what do I get? Xn. Okay. The other term I'm going to get is -3 summation n from 1 to infinity n cn xn minus 1 plus 2 summation cn xn n from 0 to infinity equal to 0. Now see what you were trying to do earlier. Okay. Now come here. Just look at the first term. You know, sometimes what happens is you need not change the index in this, you need not change the index of summation in the sense that whether you start the summation with 1 or you start the summation with 0, the series does not change. Are you getting my point? Like if you just look at this term, specifically this term, since this is starting from n equal to 1, the first term what you are getting is c1x. Yahi aayegi na? What will be the second term? 2c2x square and so on and so forth. Right? This is when you are starting your summation from n equal to 1. What happens when you start your summation from 0 to infinity? What happens to this term when n is 0? N cn xn.
0.
This term is 0, right? So that means whether I start my summation from n equal to 0 to infinity or I start from summation from n equal to 1 to infinity, the series does not change. Are you seeing the difference now? In the earlier case, it was not the case. Whether when you were starting from n equal to 0, you were getting a term c naught, which did not exist. In this case, even if I start from n equal to 0, the first term that I'm going to get is this. The first non-zero term. The other term is 0. So that means if I look at this term, whether I change the index or not, I can directly, rewrite this summation as summation n cn xn n from 0 to infinity because my series is not changing. Whereas it will not happen in this term. You can see for yourself. So in this case, we will have to change the index the way we have done in the earlier case. Why? Because there are 3 terms in this series, in this expression, and I want all the 3 terms to be starting from n equal to 0 to infinity. Are you getting the point? If you're not getting, just try writing the second term also. Just try it yourself. And you will see that if you start the second series from 1 or if you start the second series from 0, they are 2 different series. You are getting 2 different series. So that is why we cannot directly change the index of summation in this case. Whereas in the first term, we could directly change the index. So you have to be careful when you are trying. That's why I did not do it here only. I did not do it here because I wanted to specify that you have to first of all check whether you can directly change the index of summation or you have to follow that rule of, increasing or decreasing the starting point and hence decreasing or increasing the index of summation. Okay. So because we do that, that is why, what we can do here is now I can write my first term n equal to 0 to infinity and it still is n cn xn. My second term now can be written as n equal to 0 to infinity. Now we are following the same formula there. So your n gets changed to n plus 1 and you get terms like this. And your last term is still 2cn xn n from 0 to infinity equal to 0. Okay. So now you can combine all the terms. N from 0 to infinity. Of course, we'll combine the coefficients of x to the power n because I have x to the power n everywhere in all the three terms. So what will be your first term? NCn minus 3n plus 1 cn plus 1. Sorry, this is not NCn, it's like this. Plus 2cn equal to 0. Is this clear or not?
Ma'am, please explain the second term. Like if we take 1, what's the difference? And if we take 0, what's the difference?
Just write the series yourself. You write the series on your paper. What series should you be getting? Minus 3 into, I'm writing it now here, okay? N is starting from 1, right? So what you should be getting is C1. Yeah, na first term. When n is 1, it's n is 1, C1, x to the power 1 minus 1, which makes it 1.
Yes, ma'am.
So your first term should be C1. What should be
Yes,
your
ma'am.
second term? When n is 2, it should be 2 C2x, right? What should be the third term? 3
3C3x square.
square, and so on and so forth. Right? This is when you start your summation from 1. Now start from 0. What do you get? You're getting 0, C0, x to the power minus 1 plus
Ma'am, ultimately the first term will be 0 here.
but then see, okay, fine. What about terms like this? Though the coefficient is 0 here, I do not want terms like this. I want my power of x to be a positive term because it's a power series.
Yes, ma'am.
Are you getting my point? If you change n equal to 0 here, you are getting x to the power minus 1, which we don't want.
Yes, ma'am. There will be different case will arise if x is not equal
Yes.
to 0.
So since it's a power series, so all my powers of x should be 0, starting from 0. Constant term hai. So that means your n should vary from 0 to infinity. Here you are getting a minus 1 here. Forget about the coefficients here.
Yes, ma'am.
You just change 0 here. The moment you look at n minus 1, it would look like minus 1. We don't want that. Are you getting the point?
Yes, ma'am.
So that is why we have to change the index of summation there. And we get this term now. Now you can, since the coefficients are going to be 0, so NCn plus 2Cn is equal to 3n plus 1 Cn plus 1. And therefore, your Cn plus 1 is equal to, in this case, n plus 2 upon 3 into n plus 1 Cn. Am I right? So this becomes your recurrence relation. Is this clear? Now, with this as your recurrence relation, can you find the rho, the radius of convergence, and see what happens? Okay, so this I am leaving to you. With this as your recurrence relation, find rho, and then conclude when does this power series converge. Of course, this will give you a solution. You can find when n is 0, you are getting C1 in terms of C0. When n is 1, you are getting C2 in terms of C0, and so on and so forth. So you'll get a solution the way we have done it earlier. So you can write. So now what I'm leaving to you is write the final power series solution and find rho for this. Is this clear or not? Hmm? Then
Yes, ma'am.
Yes, ma'am.